Good morning, everyone, to this first open session of the PAC today. We start right away with the first speaker, who is Toshiyuki Gogami, who will present the proposal for a high accuracy measurement of nuclear masses of lambda hyperhydrogens. Please, Toshiyuki.
Thank you very much. So can you hear me?
Yes, perfectly.
Great. All right. Thank you, Chairman. So I'm going to present for the experiment of C12-1902 experiment, which is conditional experiment. I'm Gogami from Kyoto University, Japan. All right, let me start. So this shows the request summary of C12-1902 experiment, and we plan to use HRS HKS spectrometer system at hole A, and we plan to use 50 microampere beam on helium-3 and helium-4 gaseous targets. In total, so we request 13.5 days of beam time, including 2.5 days for calibration runs. And we aim to determine lambda binding energy of hyperhydrogens with world-best accuracy in order to investigate the lambda hypertriton puzzle and the charge symmetry breaking effect in the lambda nuclear interaction. Okay, so these are contents of my talk. At first, I'm going to introduce the hypernuclear study a little bit. And I'm going to introduce physics motivations for the hyperhydrogen measurements. And I'm going to move on to the experiment part of proposed experiment. I'm going to summarize my talk at last. All right, the hypernuclear study. So we study the baryon interactions. The nuclear-nuclear interaction has been investigated by rich data of scattering experiment and rich data of nuclear spectroscopy for more than 3,000 species of nuclei. So on the other hand, for the strangeness sector, such as the lambda nucleon, sigma nucleon, Xi nucleon, and so on, experiment data are quite limited, not only for the scattering experiments, but also hypernuclear spectroscopy. So far, there are only about 40 species of hypernuclei have been investigated, and the data quality, such as accuracy and precision, are also limited. And at this moment, the available facilities for hypernuclear experiments are CERN, WEEC, GSI, and JPAC, MAMI, and here at the Jefferson Lab. So now we are proposing an experiment here at the Jefferson Lab. So this shows how to investigate the baryon interaction. There are two methods. The first one is lattice QCD calculation, which is the first principle calculation. And another one is the combination of the experimental data and the phenomenological theories, such as meson exchange model, effective field theory, the core cluster model, and so on. And these two methods are complementary, actually, because in terms of precision or accuracy, method A is better for the lighter mass systems, less stringent systems, and for method B, precision is much better for the heavy quark mass systems, the large stringent systems. And this is why, so we need to promote these two methods at the same time in order to investigate the baryon-baryon interaction. And hyperons are expected to exist inside the core interior of neutron star. If strange hadrons and hyperons keep their identities in their in the neutron star, then it's quite hard to support the heavy mass neutron stars, more than 2 solar mass systems, by only 2-body force. And scientists add new ingredients to support more than 2 solar mass neutron stars, such as the multi-body repulsive force. And we believe that this multi-body force may play an important role to support heavy neutron stars. And very recently, LIGO observed a gravitational wave, and in which they observed the star massive object of 23 solar mass and 2.6 solar mass system. And if this 2.6 solar mass system is a neutron star, then it's quite difficult. It's much more difficult to understand a neutron star with hyperons. So anyway, so we need to investigate the baryon-baryon interaction on the Earth to understand the solar system, such as neutron stars. Okay, let's move on to physics motivations for hyperhydrogen measurement. And hypertriton puzzle. And hypertriton has a small binding energy, being 130 keV, which was measured in the emerging experiment. And very recently, the STAR collaboration reported the larger binding energy, 410 keV. And then we can estimate the Artemis radius of the system of lambda and deuteron by using this small binding energy, and which is about 10 femtometer. This is very large systems. It's a very loosely bound system. And by using this small binding energy and also these spatial relations between lambda and deuteron, so we can guess or we can predict the lifetime of hypertriton. And this is the one of the calculations by using FADF calculations with realistic nuclear-nucleon, hypernuclear interactions. And the lifetime is expected to be 97% of the lifetime of the free lambda. However, the recent measurement of HiFi at GSI and STAR and ALICE reported very short lifetimes of hypertriton to be 0.5 to 0.92 times the lifetime of free lambda. So this contradiction between this theoretical calculation and short lifetime measurements is called hypertriton puzzle. Okay, so this figure shows the lifetime as the function of binding energy from the theoretical calculation, including pion final state interactions in the form factor right here. And then this theory could succeeded to predict a short lifetime at the binding energy of 130 keV. However, as you see here for the experimental results for the lifetime and the binding energy, so experiment data itself, their self are very scattered like that. So we need to determine or confirm the experimental data very accurately to investigate the lifetime and the binding energy puzzles for the hypertriton. And we focus on the binding energy at Jefferson Lab. And so this error bar shows our experimental precision, expected precision. And we would like to determine the binding energy precisely like this. And if we look at immersion and STAR experiment, so they say that the binding energy is here and here. But if you look at the two-body results and three-body results, the binding energy looks to be different. This is the same situation for the STAR collaboration. So they say that 410 keV, but they made averaging for the two-body and two-body processes. And then, but if you look at the two-body, three-body processes, the binding energy looks to be different. So maybe there are additional systematic error when they make averaging to have the binding energy of a hypertriton. So we would like to determine the binding energy very precisely to pin down the Hypernuclear puzzle. This is what we want to do for hypertriton. All right, then charge symmetry breaking effect, and in the lambda nuclear interactions, it is known that charge symmetry is largely broken, and it was found in the binding energy difference between the hydrogen 4 lambda and helium 4 lambda, which are mirror hypernuclei. And if we look at the ground state binding energy, this is totally unbalanced. And at the MAMI, by using decay pion spectroscopy, and they measure the ground state of the hydrogen 4 lambda very precisely, and they obtained a consistent result with the imaging experiment, and we could confirm that there is the CSV for the ground state. But when we move on to the excited states, so this is balanced. And actually, the JPAC E13 experiment, which was reported in 2015, and they updated this energy. And actually, this is unbalanced before, but JPAC experiment is applied this energy, and it is found that this is balanced. And now, so we would like to confirm the energies of this state, hydrogen 4 lambda excited states, because this only the old gamma ray data exists for this state. And we would like to determine the energy precisely by using modern experimental method. All right. Then, so I'm showing you here the two examples of theoretical calculations for the lambda nuclear interaction CSV. And one is explicit inclusion of sigma, describing like here. And another one, phenomenological potential, CSV potentials, which was introduced by the Hiyama et al. For the cluster model calculation. And all the time when they fix or investigate the CSV interaction strength or amplitude, they use A=4 measurement experimental results as a basic input, and then this CSV potential is applied for the A=10, 7, =5, 7, 10, 9, 10, blah blah blah, heavier systems. And this is the basic way to check or to test the CSV potential. And now, so we would like to confirm the experimental results of A=4 systems, because this is a very basic input, basic ingredients to investigate the lambda in CSV. All right. Okay, so this shows how we confirm the binding energy. So there are two experimental methods, as I already explained, and JPAC will measure the gamma ray measurement, gamma ray between these two states. And for the ground state H4 lambda, ground state of H4 lambda was already measured by the immersion experiment and MAMI experiment. And it has about 100 kb error. And even if the gamma ray very good precision or accuracy, and all these excited states should have the error of the ground state, which is about 100 kb. And what we are proposing to measure is the direct measurement of these excited states by using the missing mass method. And we could achieve the similar precision to that for the JPAC. We are proposing the one-day experiment to achieve this precision. And this is very unique because, as I said, this is direct measurement of the excited states. And everything was okay. If everything is okay, and these two methods should be consistent, if not something wrong. So it should be consistent. And then, and after that, so we can say that, okay, this experimental information is fine to use the basic ingredients for the lambda nuclear interaction study. Okay, so I'm going to move on to the experimental part. And then this shows the experimental result, experimental setup for the proposed experiment. So this experimental setup is the same as that for the E12, 15, or 8 experiment, in which we are going to measure the potassium 40 and 48 lambda hypernuclei. And we are going to use HRS, HK system. In front of these two spectrometers, we are going to install PCS, additional magnets, pair of charge separation dipole magnets. And we've already constructed PCS in Japan, Japanese company Tokin, in March 2020. And basically, we are ready to transport PCS magnets to the Jefferson lab. And in addition to this experimental setup, so we are proposing to have the helium-3, helium-4 gaseous targets for physics round, and for the calibration round, so we propose to have the hydrogen gas and multiple targets and an empty target for the calibrations. And target ladders for these gaseous targets may be separated from the others, such as calcium targets. So we need to have discussions with target group. for the detailed design. Okay, so this shows the very rough schematics for the target. So we have the H target, helium target, empty target, and portfolio targets right here. And the hydrogen gas target is a little bit larger than the physics target because we want to calibrate the whole volume of helium targets. So that's why hydrogen target is a little bit larger than the other targets. And we have chosen the Tunakan type of cell target in order to minimize path length of the particles in the aluminum cell, and leading to the minimizing the multiple scattering effect in the target material. And we are going to select the center part of the target in order to achieve the beta signal to noise ratio. So we would like to avoid the aluminum contamination. Okay, and we performed the GR4 simulations in order to predict the missing mass resolution. And we constructed the GR simulations for the E127003 experiment, in which we used tritium target to investigate the lambda neutron 3-body systems. And we could reproduce the binding energy resolutions for lambda and sigma like this. And basically, we add the PCS in this GR simulation to estimate the missing mass resolution. In the simulations, at first, we reconstruct Z vertex like this formula, and then this Z vertex information is input to the matrix for the momentum vector calculation, and then we estimate the missing mass resolutions. So this shows the momentum and angular resolutions for the HRS and HKS by using this analysis. And of course, we also need to take into account the materials like a target material, detection materials, and everything is in this GR4 simulations. And at last, so we estimated the missing mass resolutions to be 1 MeV FWHM, which is fairly good enough. Okay, yield estimation, and exactly same reactions have been investigated in Hall C, Jefferson Lab. And then at forward angle, the cross sections was deduced to be 5 nanobar/s radian for hypertoroidal production and 20 nanobar/s radian for the H4 lambda production. And then we estimated total yields like this. Okay, this shows you the expected spectra for hypertoroidal and H4 lambda, and we estimate statistical error is less than 20 keV. Okay, I'm going to skip in detail about the calibration, but the calibration is quite important for this experiment because we need very accurate measurement of binding energy. And yes, and the main component for the binding particle error is energy scale calibration, which is about 50 plus minus 50 keV. And actually, so this method is already developed in the past hypernuclear experiment, which is about 50 keV uncertainty. And important thing is the energy loss correction. So as I said, we're going to employ the Tunakan type target cell and then so we aim to keep the target density uncertainty plus or minus 3% and cell thickness and uniformity plus or minus 10%, which is the very realistic assumptions. Then systematic error is estimated to be 70 keV in total. Okay. All right. And then of course the purpose for the hypertoroidal measurement, hypertoroidal puzzle, but not only for that, but also we can provide a very important information of the lambda-nuclear interaction itself. It shows the scattering length as a function of the binding energy of hypertoroidal, and there are theoretical predictions like this. And if we make a plot like this with the experimental error, and then we can, when we project these information to the vertical axis, and we can make limitations for the scattering length between lambda nucleon spin singulated state. All right.
Sorry, your time is up. If you could please jump to the conclusion.
Yeah, sure. Thank you. So this is the beam time request summary. For calibration, we requested 2.5 days, and for the physics round, total 11 days. And in total, 13 days, 5 days are requested. Okay, that's it. Thank you very much.
Thank you very much indeed. So I pass the word to the first reader of this proposal, that is Charlotte Elster. Please, Charlotte.
Okay, so let me just, supposedly you would be starting now, or, get a go-ahead. When would you actually have results which you could give hand off to a theorist?
I'm sorry, so...
No, so you prepared everything and stuff, and supposedly you were scheduled next year. Yeah, let's be optimistic, beginning 2021. With analysis and everything, when would you actually could give some definite answer or to a theorist to continue to work with?
Different answer for...
No, it's along with the experiment, analysis, and everything, with all the care you do, how long does it take?
That's a good point, yes. So we are going to introduce the new magnets, and probably it takes some time to calibrate it very precisely. Of course, the first result will come up in 1 year or 1.5 year, but we need to fix the systematic error. So it's hard to answer, but we aim to obtain the final result in 2 years or 2.5 years.
Okay. Now, in case, this time I'm also you put on the slide, Yama-san, Kamada-san, and the group in Yuri, they're somewhat waiting on what your, for example, your fixing of your estimates on the scattering lengths eventually are going to be, because your picture already shows very nicely that several interactions will be just ruled out. So that's why I say, if you're going ahead, that you still, it will take its time and care to do it. But you said, so do I get you right? If you from the point you are allowed to run, it would be roughly taking 2 years. Do I get this correctly?
Yeah.
Okay. Thank you.
Thank you.
If Charlotte doesn't have any other question, I would ask Shinya Savada to ask if you have any question. Please, Shinya.
Yes, well, this might be a minor question, but my question is on the target. So, have you started the discussion to design the target with target group already?
Actually, we've talked to the Dave Meekins and Sylvie a little bit, but we didn't discuss any details. So we discussed about the rough concepts, how to install our target systems, including other targets such as calcium targets, and also, so we are, as you know, that we are proposing other targets, the lead targets and the tritium targets, and yes, so we have many constraints, and then we share these information with the target members. And actually, this is it. We didn't talk in any details yet.
All right, but the rough response at this point is your target is doable, right?
Yes. Once PAC, yes, they say okay. Yes. They say that okay, they will manage they will manage to make targets. They say something like that. Yeah.
All right. Thank you.
Thank you.
Any other question from a member of the PAC? That does not seem to be the case. Is there any urgent question from the audience? If so, please type it into the Q&A box. Doesn't seem to be the case either, so I suggest that we thank the speaker very much and switch over to the next speaker.
Thank you very much.
is Professor Tang, who will present an extension request for E12-17003 for the unknown lambda-n interactions. Please.
Can you see my full screen?
Not yet.
Let me retry it again.
Now we see it all right. Excellent. Please go ahead.
Is it full screen now?
Yes.
Yes, perfect.
Okay. This is Li Guangtang from Hamilton University and Jefferson Lab. This proposal is a request to further make an extension request to run this E12-17003 again to determine the unknown lambda-neutron interactions by investigating the lambda-neutron-neutron resonance. This experiment is already done in December 2018. We spent a year analyzing it. Currently sending out for publication. Publication is under review. The previous speaker already introduced the concept of hypernuclear study. I'm going to make short. So overall goal is study the baryonic interaction beyond, try to include all flavor. So the charge symmetry breaking is one of the unresolved puzzles. As a previous speaker already mentioned, the nuclear interaction charge symmetry breaking find negligibly small. And so with good approximation, you can exclude to the charge symmetry breaking. However, from the A=4 system, for the lambda nuclear interaction, in terms of binding energy of hydrogen 4 lambda, helium 4 lambda, significant charge symmetry breaking was found, and actually almost several times larger and non-negligible. And the origin is still unknown, although theoretically, there are publications claiming that lambda sigma coupling is could be responsible and had a good agreement for at least A=4. Now, to resolve this puzzle, certainly direct scattering data is extremely important and needed. So in case of a nuclear interaction, there are plenty of data. And in terms of lambda proton scattering, there are data, but very limited. In terms of a lambda neutron scattering, there's no information, no data exists at all. Practical means short lifetime of lambda, there's no lambda beam, and there's no free neutron target. So based on the missing of this important information, rely on ignoring the charge symmetry breaking, the lambda neutron, lambda proton interaction so far been treated identical in all the models in interpretation of existing hypernuclear data. So now, the goal of the previous experiment is the same as this one. So this one does not changing overall goal. The goal is actually using the unique E'K reaction, mass spectroscopy, combined together with excellent CBEF beam. And at that time, the tritium target was available to searching for the possible lambda neutron-neutron resonance. This is after the hint given by Hyphi at GSI, publication claiming based on the decay time, claiming there is possible bound lambda neutron states. Although extensive theory study shows excluded such possibility for bound lambda neutron system. Additional theory study using a pole search type of theory technique to show that all the current leading models does not support bound states, but subthreshold, which is unphysical resonance, which is supposed to be broad, shouldn't be seen. However, using this pole search type of technique by separating the three-body potential into two-body neutron and lambda neutron, and of course start with the lambda neutron potential start with assuming lambda proton, and then gradually increase the strength of lambda neutron apart 2.5% step to get a full spectrum of the eigenvalue of the Fedivas equations solution. Find that almost all models agree that about a 5% increase of the lambda neutron strength, the real resonance does appear. So that gave a strong hint that for the first time experimentally, we can determine the unknown lambda neutron potential by investigate the lambda neutron resonance. The way to do so is try to give a good precision measurement to the binding energy, find the resonance, measure its binding energy and its natural width, and then try to extract the lambda neutron interaction. So this shows practically this actually is possible for the first time experimentally to give this lambda neutron type of experimental information, which is extremely important. Now, of course, experimental condition, the cross-section is unknown because this is never measured before. And at that time, for this previous experiment, HRS coupling, the two-arm coincidence, the system is not optimized for E prime K reaction because the HRS is very long path length and the acceptance is very small. At that time, with optimized consideration, we hope within the proved time, if we can get 120 counts with a resolution better than 2 ME to 4 West half maximum, if the state does exist, then we can have accuracy, binding energy better than 100 keV, the natural width better than 70 keV, which is essentially good enough to give a theory that good constraint for the first time to determine the lambda neutron interactions. Here, let me show the result after 1 year of analysis. This is the spectroscopy, and the green part of the histogram is accidental. This accidental is not come from the kaon, but imperfect is particle identification because of a mixed with pion background and proton background, because HRS doesn't have good particle ID for the kaon, particularly at a momentum over 1.8 GeV. Beta is almost 0.99. It's very difficult to separate kaon against pions. The aerogel detector, the PMT, is almost dying. Average single photo electron is only around 2, so it's very difficult. So this is actually pion proton background. The solid line is quasi-free, and you can see that the sigma quasi-free, because of limited kinematic acceptance, the sigma quasi-free is severely cut off, basically almost completely cut off. On top of the around 50 MeV at the excitation, there's a 2% of hydrogen contamination, so which we verified very well for the lambda peak under hydrogen analysis with and agreed with other treating experiment. At the threshold, near the threshold, we find that there is a possible observation, the first peak, a possible observation of the lambda neutron-neutron resonance. We determine based on the resolution analysis, we determine that the natural width is 0.55 MeV. So this is possible, the observation, but the statistics is extremely low. So for better determination, definite identification is very difficult. Although there's a second peak also observed, and this actually quite strange. It's unexpected in terms of its position and also in terms of its width. It could be actually it's a broad resonance. It could be a broad resonance, but somehow due to low statistics appeared like this, or maybe due to some other reason. So these also need to be confirmed. What we notice that if it exists, and the cross section is very, very small. So the previous experiment, the uncertainty is quite large. Now, on the other case, by putting a wider beam size, and you can see the first two peaks still have a signature there, but what we notice that there is a quite extensive enhancement just below the sigma threshold. And this actually indicate that there is also a strong likely possibility for the first time we observe the A=3 bond sigma nucleon states. This is actually a bond state. So the binding energy estimated is around minus 1.7 MeV. The full width half maximum is a little bit over 5 MeV. And this compare with only states, bond states found in A=4. Binding energy is around 4 MeV. The width is around 7 MeV. And so although the theory has been predicting exists for A=3, but never been found. And so in K-pi reaction, there's no A=3 bond state found. And early Jefferson Lab experiment, E91016, also didn't see from a helium target. By overall this analysis, we suggest that this might be the first time we see A=3, but also a sigma-0 neutron-neutron states. And this might have some connection to the lambda neutron-neutron system. And this is also additional interest and also highly interest. So because of this, we feel that summarize the previous experiment, we find that it's certainly very exciting that find possibility of such states. And if we put some that value into this study, we find that it looks like it does that a lambda neutron interaction is stronger than lambda proton, but the uncertainty is so large, is making such measured position much less meaningful in terms of giving constraint to theory to pin down this interaction. So therefore, it's much meaningful to redo the experiment and shrink this number one to confirm solidly such resonance, and as well as the A=3 bound sigma hypernuclei, but also significantly reduced error bar to making sure to give a theory sufficient constraint to final determine the lambda neutron interaction. So that's why we propose to extend this experiment and run it again with optimized the HKS-HRS combination, and to run together with E12 1508 on calcium 4048, and just give additional beam time and put tritium target back in. Of course, it's a new tritium target. The yield estimate we say there's a comparison why we say this is much better optimized with a smaller scattering angle. From instead of a 13.2 degree, and this time it's a 6.5 degree, the virtual photon flux increased more than 7 times. And
you have 5 minutes left.
Pardon me?
You have 5 minutes left.
Yeah, I'm almost done. So with a short path length of HKS at one point, even at a lower momentum, the K-on survival rate is almost 3 times larger. The HKS has excellent KID, so K-on is almost 100% cleanly separated, and also with almost more than 90% of detection efficiency. So very, very small K-on loss. So that can increase another 50-60%. And also HKS has a very large kinematic acceptance that not only accept the entire lambda quasi-free, but also almost fully the sigma quasi-free. That also help to determine the sigma bound states for the A=3. Of course, the target will be shorter because the target chamber is smaller. So previous experiment, 25 centimeter long, we proposed using 16 centimeter, but identical design. So by this, we already consulted with the target group together with a previous speaker. We already discussed with target group, and it looks like mounting gas target is not really a problem. But the matter is how to cooperate with all the required target, as long as we are using gas target, not include any liquid target. Overall gain is about 22 times. So that means with a shorter required 8.5 day, including the calibration. Previous experiment proved 12 day, but this is we require only 8.5 day. But we can the first resonance only about 15 counts, but we can get more than 250 counts for the lambda neutron resonance. And the sigma bound states, we can have more than probably 800 counts. These are very significant. Statistical uncertainty now will be reduced significantly to below plus minus 50 KED. The overall systematic error, similar as the previous experiment, we are calibration almost the same, using the similar technique. So systematic error should be contained with below 70, plus minus 70 KED. So the breakdown of the hours, the tritium run is 140. The hydrogen run for calibration is 8 hours. We will use a multifoil target using the ground states of boron 12 lambda, which is well measured. We give extensive calibration to ensure the optics are well calibrated and optimized. So this was not done for the previous experiment, although we achieved a 1.8 MeV full width half maximum resolution. For the future experiment, because of a smaller scattering angle, the multiple scattering over the aluminum cell will be more severe of the scattering angle. Resolution will be lower than the previous experiment. However, achieving better than full width half maximum 2.5 is still very confident. We have a technique, we have experiment. So the other thing is for background, empty cell, and these are basically all the similar as before. The only difference is we add extensive calibration using the carbon foil target for also for other calibrations. Overall summary, I want to emphasize that previous experiments have proven the feasibility and uniqueness to use E'K reaction with tritium target to carry out such extremely interesting topic experiment. So experiment had a possibility observed the lambda neutron resonance, and also surprisingly, for the first time, we may also find a bound sigma neutron nuclear states. However, obtained better statistics. The statistics was too small from the previous experiment, allow to definite identification, but nor being able to provide constraint to the theory at the previous level. Now, the new experiment proposed with identical object motivation, but optimized HKS, HRS. And I believe with the potential a major discovery is worth it to bring the tritium target back again to run, and to hope to reduce significantly the statistical uncertainty to below 50 keV. So that's all I want to say.
Thank you very much. And we proceed as last time. The first reader of the proposal is Charlotte Elster. So Charlotte, it's your time to ask questions, please.
Yeah, I mean, it's, you could go back to your target, because some of the technical concerns are, though there had been a tritium target before, you are changed the target now, it's shorter, you gain more, but the concern was that the new specification of the target needs to be kind of a new scattering chamber and stuff like that, and all the procedures for safety for a tritium target also has to be redone. So it's not, you make it sound very easy that you just swap the target, but the concern that that it's not the case. Do you have any comment to that?
Yeah, this we already consult. This is my also concern. So that's why we discuss this with target group, particularly for the safety measure. What common from target group is the safety measure itself is not a big issue. They say that in terms of space, implement all the safety measure, including a security fan and so on. That apparently not a big issue. The target group, the main concern is how we utilize the space to actually housing all these targets. So that need to be careful and work together to work it out. That is what I got from the target group. So I first concerned with the safety measure because previously there are a lot of procedures, and I wonder whether based limited space there, whether this will be a trouble. But my answer from target group was not, at least it's not a showstopper. It's manageable. Of course, switching. If this experiment to run again, certainly this should be scheduled at the very last. When all the HKS experiment finish, then certainly there should be almost 10 to 12 days of shutdown to bring the target in and start how it's locked. So there's a transition from the normal HKS run to this last experiment with tritium. There will be certainly at least a minimum a week shutdown to put the tritium targets in. All right. So this is certainly an issue, but this is not unworkable issue, but it's manageable. It's just a procedure. So.
Okay. They also said, I mean, it's and your proposal doesn't contain that also. I mean, it is a gas, and so I mean, the gas has very variable densities and stuff. Did you do simulations about density loss for the production in that tritium cell under normal conditions, and how does it affect your luminosity and how does it affect your intensity? We did not see that in your proposal.
The reason I didn't include that is based on the previous experience. Remember, the previous experiment was the last experiment using the tritium. So the tritium target cell has been extensively used by previous experiment. And at the very last, we use it because this is to our experiment is a mass spectroscopy. So the density also is varied because we are not interested in cross section. We measure actually the mass, even the density gradually decreasing. But for example, the previous experiment, the target cell was extensively explored by first experiment running more than 2-3 months. And we are the last one run only the last 3 weeks. And it didn't really matter much. And our yield is, so for the next experiment, we will be the first one to use it and only use 8.5 days. So I don't think this actually matter to us at all.
Okay. Then they also, I mean, okay, so if I see your picture, you have to have a hole in the target or somewhere for the beam going in. Is that accounted for already in the design? And how do you have to also do cooling, which is also not mentioned in the proposal?
Yeah, the tritium target is the same as the other gas target. The previous speaker proposed helium-4, helium-3. All these gas target has to be cooled. So, but they are not a liquid target. So cooling this target using the standard cooling. Just like a previous tritium run.
Okay, so
it's identical as a previous experiment.
Okay, so you did not include it in the proposal because this is kind of like a standard setup that a gas target needs cooling, and this is kind of like you have your refrigerator at home.
Right. No. This will be managed by target group. Just like a normal running gas target.
Okay.
So the carbon hole target is the standard as a standard target when running the tritium. When running the tritium experiment, every time the beam comes back, we have to bring the carbon hole target in to making sure the beam is correctly the direction, to clear that central cell area. Then we switch over to tritium run. That is almost the standard procedure when we operate the tritium target in 2018. And that one doesn't really cost overall a lot of time because every time you come back, just a couple of minutes, you replay the data, you find the geometry, the beam location is fine, then you switch to regular run. Overall add up together probably just less than an hour for the entire running period. So that's why I didn't put it here.
Okay, thank you.
Let me point the PAC members to a small comment in the Q&A box. You might want to take a quick look at that. Shinya, do you have any questions to ask?
All right. Okay. So, do you have an urgent competition about the lambda-NN or sigma-NN physics?
Say it again. I didn't understand.
Okay. So, do you have any competition with another experiment in Europe or Japan in lambda-NN or sigma-NN? Maybe no.
I see what you mean. I believe that in GSI, because of, we are running this certainly fuse agent, and suddenly this becomes a hot topic. And I believe that GSI, they're upgrading their magnet, they're they probably want to redo the HyPhi experiment, adding equipment. But I don't know, number one, I don't know when they're going to run. Certainly, I think they are trying to do a better experiment than the previous HyPhi. But my feeling is the basic way to run it, principle, is still the same. It's a heavy, relativistic heavy ion collision, and they have to utilize the decay particle to reconstruct the missing mass and the lifetime, using the lifetime to determine whether it's a bound state or not. In terms of resolution, I don't believe they can reach the type of resolution we can have, particularly measure the binding energy and natural width as precise, the same level as we are. The only difference is they can measure lifetime, and we cannot. We just simply measure the missing mass. We have certainly much better resolution. However, in terms of urgency, in terms of physics, the interest, and these actually for them pop up, really want to redo it. How soon they can redo it, I really don't know. Could be 2 years, could be 3 years. They want to, because they really want to add a new equipment, major upgrade. So in order to do it, could be 5 years. I don't know. There is so to such extent.
Thank you. I think that point is quite clear now.
Yeah.
Sorry to interrupt, but we do have to rush on with the agenda. Is there any other question from the PAC?
Marcus, I have a comment.
Please, yes.
The slides are not posted on Indico. The PAC needs to have the slides posted on Indico to discuss this experiment in the executive session that we are about to start.
Yes.
Is that clearly understood, Li Kuang?
So I should send the slides to someone?
You can send them to Susan Brown, or you can post them on the Indico, but the PAC needs your slides to consider your experiment.
Yes.
Okay, probably I will email to Susan.
Thank you very much.
I have actually a very short question also.
Please go ahead.
Is it a correct interpretation of the measurement that you did that the cross-section is about an order of magnitude smaller than your previous proposal?
Yeah, something like 7 times smaller.
So the cross-section is actually if the state exists, the cross-section is very small.
Yeah, very small. So
okay.
In the nanobar type.
Okay, thanks.
Then let's close this session. Thank you again for all speakers and participants. The open session will resume at 11, and the PAC will meet straight away again in the closed session. Thank you very much.